Okay, we are starting our notes in the redox unit. So redox stands for reduction oxidation, and we're going to go back to roughly unit 4 when we started assigning oxidation numbers to elements. When we looked at nonmetals, I told you to ignore the charges of nonmetals that weren't the first one. So for a lot of nonmetals, they have multiple charges, and we're actually going to explore where those multiple charges come from when they bond in this unit. So looking at rules for assigning oxidation numbers, if we have an element that has not bonded with something else other than itself, it has an oxidation number of 0. So as you hopefully remember from oxidation numbers, they are assigned from a gain or loss of electrons. Well, if something other than bonding to itself hasn't bonded, it's not gaining or losing any sort of electrons yet. So they would have an oxidation number of 0. Looking further on our periodic table, there's certain elements that are pretty stubborn with their oxidation numbers. So in order from A to E, the oxidation numbers of group 1 metals are always +1. Above all else, group 1 metals are +1. Group 2 metals like to be +2. Hydrogen loves to be +1 unless it bonds with a group 1 or group 2 metal that forces it to be something else. Oxygen likes to be -2, and group 17 is -1. Now these again are in order. So A is the highest priority of group 1 being +1, and then going down to group 17. Everything else, every other element, when it's bonded to one of those things, will manipulate its oxidation number to make the compound what we call neutral. So that's the next rule, which is neutral compounds' charges must add up to 0. So looking back at a couple things, free elements are 0. That's one that I typically see students forget as we go on. A lot of people will try to pull, like if I have oxygen by itself, they'll tell me oxygen is -2 instead of just being 0. So just be careful with that. With the neutral compounds charges adding up to 0, that's why we crisscross. So when we crisscross, it actually ends up working out where our charges end up equaling 0 through that method. So looking at this, calcium here is +2. We get that from our reference tables. It is a group 2 metal. So if we look at our reference tables, calcium is a +2 charge, and then bromine will be whatever it needs to be to make that equal 0. So when I look, I have one calcium having a +2 charge, and then I need bromine's total charge to then equal -2, so that this equals 0. I have 2 bromines, which means each bromine is going to be -1. For polyatomic ions, they carry a charge. So our table E polyatomics, they have their own charge associated with them, like SO4, NO3, NH4+. So if we're looking at, for example, SO4, instead of the charge adding to 0, it adds to the charge of the polyatomic. So for example, SO4, the charge of that compound is -2. So if I look here, of my rules, group 1 is +1, group 2 is +2. That's not SO4 or O4. Oxygen is almost always -2. So oxygen will take on that -2 charge. And there's 4 oxygen, so that overall has a total charge of -8. In total, this compound needs to equal the charge of the polyatomic. So that -2 charge, that means sulfur, in order for this to equal -2, has to have a +6 total charge, and there's only one sulfur. So it would have a +6 charge. It says some elements can have several possible oxidation states. For these, you need to calculate the oxidation state. So that's what I was talking about with our nonmetals mostly, is the scenario for that. Like nitrogen has many, many oxidation states. We need to figure out what form is nitrogen taking when it bonds to whatever it is. Same with manganese. If you look at manganese on our reference tables, manganese is a transition metal. It has 4 different options. So when it bonds with potassium and oxygen, we need to figure out what it can be. So how we do that is if I have KMNO4, I'm going to use my rules. So potassium is a group 1 metal, which the very first rule is that group 1 metals get to be +1. So potassium in this scenario gets to be +1. there's 1 potassium. So as I go down, I'm going to multiply the oxidation number, which are my top numbers, by the number of potassiums there are to give me what's the total charge. So for example, for potassium, I have 1 potassium and it has a +1 charge, so in total, all the potassiums in that compound have a +1 charge. The next one I'm going to do, out of my rules, if you look, manganese is not in my rules, but oxygen is. So oxygen is almost always -2. So oxygen's oxidation state is -2, which is going to go on top. And then again, as I'm going down, I'm going to multiply. So -2 times 4 gives me -8. So that's the total charge of all the oxygens is -8. This whole compound I want to equal 0. So basically I'm trying to find out what this manganese is, or that X is. So -8 and +1, the only way I can make this equal 0 is if manganese is a +7. And there's only 1 manganese, so that one singular manganese has a +7 charge. So essentially, as we're doing this, as you go down, you're going to multiply by the number of elements I have. So for example, the oxygen, I took that -2. I have 4 oxygens, each with a -2 charge. Those will have a -8 total charge. If I go back up, once I know the total charge, I can go back up and find the individual oxidation state of each element. I'm going to divide. So again, looking at oxygen, I have a -8 total charge for all my 4 oxygens. Divided by 4 of them means each oxygen has a -2 charge or oxidation state. Okay. So what you guys are going to do right now is take a second and you're going to do specific questions in here. So do B, C, E, F, B, C, D, and B, D. So take a second, pause this video, and then when you are ready and you have done all of those, play the video again, and I'm going to go through every single one of these. You can check your answers. I'm going to put the answers up first. So if you are good with your answers, you can go ahead and skip past this part to the next part of the video. So go ahead and pause. Okay, here are the answers to those specific questions. And again, if you understood this, you can go ahead and move on to the next part of the video and skip going through how I got these answers. But if you need a second and want to hear again how I went through and got all of these answers, stay with the video. And I'm just going to go in order. So for 1B, for example, SO3. So if I notice here, there's no charges listed on any of these compounds, which means the total charge of every single one of these compounds is going to be 0. It asks me to find the oxidation state of sulfur in each of these compounds, so I'm going to start again with SO3. So oxygen has a -2 charge. It's very stubborn about that. So oxygen is -2, which means its total charge, 2 times 3, is -6. I want this to equal 0, so the only thing that's going to neutralize that -6 charge is if sulfur is +6. Going back up, there's only 1 sulfur, so I'm going to divide +6 divided by 1 gives me my oxidation state of sulfur is +6. For SO2, again, oxygen likes to be -2. I'm going to multiply going down, so -2 times 2 gives me -4. Sulfur, then, in order for this to equal 0, has to be a +4 charge. And I'm going to divide going back up, so I have +4 and only 1 sulfur, so that sulfur is going to take on that +4 charge. For Na2S2O3, sodium is a group 1 metal, so that's our first rule, is group 1 metals like to be +1. So going downward, in total, sodium has a +2 charge. Oxygen is also very stubborn with its charge, so it's going to be -2. -2 times 3 gives me -6. and I again want this to equal 0. So I have a -6 charge, I have a +2 charge, which means that overall the total charge of sulfur has to be +4. I'm going to go back up to find the oxidation state of sulfur, so I'm going to take +4, divide by the number of sulfurs I have, which is 2, which gives me an oxidation state for each individual sulfur is +2. So in total, essentially, sulfur lost 4 electrons, the 2 sulfurs, each of them losing 2. And then for 1F, sulfur by itself is just 0. So as a reminder, anything by itself is 0. It has not gained or lost electrons in that process. So same with number 2b, that chlorine has a 0 charge. For sodium chloride, it's asking me to find for 2 the chlorine of this compound. Sodium has a +1 charge, which means in order for this to equal 0, chlorine would have a -1 charge, and there's only 1 chlorine. And then for HClO3, oxygen likes to be -2, which gives me a total charge of -6. Hydrogen likes to be +1, which means chlorine, in order for this to equal 0, has to be +5, and there's only 1 chlorine, so that chlorine will take on that charge. And then to find nitrogen and HNO3, oxygen likes to be -2, which will give it a -6 charge total. Hydrogen likes to be +1, which means that nitrogen is going to be +5. Okay. For skill number 2, identifying redox reactions. So it says, how do I know if a reaction is redox? It says, in all reactions, both mass and charge must be conserved or maintained. So we learned about conservation of mass and charge and energy in previous units, so this is coming back. It says, and if an equation involves a free element, an element by itself, it is a redox reaction. So if we have some sort of element by itself and then it reacts, that's going to involve a redox reaction because as it reacts, it's either gaining or losing electrons as it does so. This says double replacement reactions are never redox, but the other 4 types usually are. So a lot of times on the Regents they'll ask you which of these reactions is a redox reaction. So you can eliminate any reactions that are double replacement, and then you're going to have to go and look at oxidation states to determine the other reactions. So redox reactions involve elements that change oxidation states from reactant side to product side. So just keep that in mind as we're looking at types of reactions. We're going back now to Unit 5 with our 5 different types of reactions: single replacement, double replacement, synthesis, decomposition, combustion. Double replacement never is, but the other 4 typically will have some sort of redox going on. So it says oxidation reduction reactions are reactions in which one type of atom increases in oxidation number and another type of atom decreases in oxidation number, and we call that oxidation reduction, which is where we're getting redox, so reduction oxidation. And it shows a redox reaction. First steps to determine if a reaction is redox, the only way we can do that is by looking at the oxidation numbers. So we're going to look at the oxidation numbers of the reactants and then compare them to the products. So if you look here, it says for the example, step 1 and step 2, you're going to assign oxidation numbers for the reactants. So for example, sodium is by itself, so it's 0. Chlorine by itself is 0. And then they bond. And then when they do that, sodium takes on a +1 charge, chlorine takes on a -1 charge. So if we compare sodium from the beginning of the reaction to the end of the reaction, if you notice, sodium lost an electron because it has a +1 charge. Chlorine gained an electron because it has a -1 charge. That is a redox reaction because we have different elements changing oxidation numbers. One of them is increasing in oxidation number, one of them is decreasing in oxidation number. So this says, do the oxidation numbers of the atoms change before the reaction? Yes. And if you look here, it tells us sodium has a charge of 0, but then it's oxidized to +1. So the reason why that's oxidized is because if we look back up here, we said increased in oxidation number is oxidized, and that a decrease in oxidation number is reduced. So think price reduction. A decrease in price is a price reduction. so that's reduced. And then oxidation number, when that goes up, that's oxidized. So sodium, because it went from 0 to +1, its number went up, it's oxidized. And then for chlorine, it went from 0 to -1, that's going to be reduced. So it says, is the above reaction redox? If so, why? Yes, it is a redox reaction because we have those changing oxidation numbers. So these are some tricks to look out for. So look for pure elements, meaning elements by themselves, which we had sodium and chlorine. Single replacement and combustion reactions are always redox, so if you see either of those types, you can know it's redox. And then synthesis and decomposition reactions are typically redox reactions. You have to look a little bit closer at those and actually determine the oxidation numbers. So for example, this reaction with the sodium and the chlorine, that's a synthesis reaction. We had to look at the oxidation numbers to make sure they were changing, one increasing, one decreasing. So, same thing. Take a second, pause the video, and answer all these questions, number 1 through 10. And then once you are done with that, I'm going to put the answers on the screen in just a second and explain the answers. So again, pause the video, answer them, and then once you're done, play the video again for the answers. Okay, here's the answers to number 1. So it says, which equation is an example of an oxidation reduction reaction? So if I were to just simply identify the types of reactions I'm looking at, number A, the option A, is single replacement, and the reason why is I have a singular element reacting with a compound. Option choice C is a double replacement because I have two compounds reacting. That we said is never a redox reaction, so we can eliminate that. Option B is an acid-base reaction, which is also a form of a double replacement reaction. It's just a special form of it. So that is never going to be redox. And then option D is also a double replacement reaction. So by process of elimination, single replacement reaction, which is option A, those are always redox without even having to identify all the oxidation reduction or oxidation numbers of each of the elements. We're able to determine which one's a redox reaction. In a redox reaction, we have conservation of both mass and charge. Mass meaning if I start with 1 copper, I better end with 1 copper. Charge meaning I'm not gaining or losing electrons randomly. Like the start of my reaction, if it starts overall, all the elements together started at a -2 charge, they better end at a -2 charge. Or if they all started completely neutral, each of the compounds neutral, they need to somehow end neutral. And you'll see that as we go. We'll get into that a little bit later. For number 3, it says balance each reaction, classify each reaction, then determine if it's redox or not. So for the balancing, I'm going to talk you through loosely, but if you're struggling with balancing, you are going to have to go back to your notes in Unit 5 for balancing reactions. So for this, I have 1 aluminum on the left, 1 aluminum on the right, that's fine. 1 copper, 1 copper, 2 nitrates, 2 nitrates. So this reaction is written as balanced. Classification-wise, this is a single replacement reaction, because I have 1 element reacting with a compound. In number 4, I have 1 barium, 2 chlorines, 1 chlorine, so on the right I need to put a 2 there, so I have 2 chlorines, 2 sodiums on the right, 2 sodiums on the left, 1 CrO4, 1 CrO4. So that reaction is now balanced, and that is a double replacement reaction because I have 2 compounds reacting together. For number 5, I'm going to write water as HOH since I'm seeing it split up kind of that way over here. So on this side I have 3 hydrogens, on the right I only have 1 hydrogen, so I'm going to put a 3 in front of here. Now I have 3 hydroxides. I want 3 hydroxides on the left. I have 3 potassiums. I want 3 potassiums, 1 phosphate, 1 phosphate. So now my reaction is balanced. That is a double replacement reaction. It's also an acid-base reaction, which again is just a special form of double replacement. For the next reaction, I have 1 calcium, 1 calcium, 1 carbon, 1 carbon, 3 oxygen. So that reaction is also balanced. This reaction is a decomposition reaction. Decomposition reactions are sometimes redox reactions, which means I need to look up its oxidation numbers in order to figure out if it is a redox reaction or not. So calcium is a group 2 metal. It likes to be +2. When it's by itself, which it's not at all, never mind. Oxygen likes to be -2. Overall, that would be a -6 charge. Calcium would be a +2 charge, which means carbon has to be +4. Over here, calcium likes to be +2, oxygen likes to be -2, and if I look at total charge-wise, that works out. And then CO2, oxygen likes to be a -2 charge, which means overall it would have a -4 charge, carbon has a +4. So what I'm looking at is, does calcium's oxidation state change? It goes from +2 to +2. It doesn't change. Carbon goes from +4 to +4. It doesn't change. Oxygen in both scenarios stays at -2. So this number 6 is not an example of a redox reaction because it has no changing oxidation states. Okay, we'll get into classifying redox for the other reactions in a second, but that one specifically is not a redox reaction. For N2 and H2 going to NH3, that is a synthesis reaction. Synthesis reactions are sometimes redox reactions, so again we need to determine oxidation states. The oxidation state of N2 and H2, because they are by themselves, is 0. And then hydrogen likes to be +1, so that overall will take on a +3 charge, which forces nitrogen to be a -3 charge. So strictly looking at oxidation states, nitrogen goes from 0 to -3. That is going to be decreasing in oxidation number, and hydrogen goes from 0 to +1, which is increasing in oxidation number. Balancing this, since we didn't balance it yet, I see 2 nitrogens on the left, so I want 2 nitrogens on the right. And then I see 6 hydrogens on the right, so I need 6 hydrogens on the left. Redox-wise, this is a redox reaction because of what we just talked about with the changing oxidation numbers. For CH4 and O2, that is a combustion reaction. So O2 is by itself, so that is 0. Hydrogen likes to be +1, so that would take on a +4 charge, which means that's 0. And then carbon would be -4. Over here, oxygen likes to be -2, that would be -4. Carbon would be +4. And then hydrogen likes to be +1, oxygen likes to be -2, and if I look, that works out fine. Now, if you remember, back up here really quick, we said that single replacement and combustion reactions are always redox. So without me even looking at oxidation numbers, once I identified that it was a combustion reaction, I could have said, yes, this is a redox reaction. Proving it with the oxidation numbers, carbon goes from -4 to +4, so that changes oxidation number. Oxygen goes from 0 to -2, so that also changes oxidation number. So looking back up here, single replacement reactions are always redox reactions, so without even looking at oxidation numbers, we could say yes to that. And double replacement reactions are never redox reactions. So again, without looking up oxidation numbers, we can just say no. A redox reaction is one in which reduction, and oxidation occur at the same time. So it's a simultaneous reaction. And then this says oxidation reduction reactions occur because of the competition between particles 4. We're competing for electrons here. So they're exchanging electrons throughout that process, which is why they're getting positive and negative charges. Okay. On to part 3. So skill number 3, identifying species, oxidize, and reduce. So now we've kind of built up Once we know the oxidation numbers, we just take it one more step further and we look at the oxidation numbers and say, is the oxidation number increasing or did the oxidation number decrease? And that will help us determine what was oxidized and what was reduced based on if the oxidation number increased or decreased. So looking at that same example, for this, sodium changed from 0 to +1. So that oxidation number increased. Chlorine changed from 0 to -1. So that oxidation number decreased. It says, once you've determined a redox reaction, you need to pick out what's oxidized and what is being reduced. Losing electrons results in an increase in positive charge. So we're becoming more positive. Increase in oxidation number is oxidation. So out of sodium and chlorine, the one that increased in oxidation number was sodium. So that is what we call oxidized. This underwent oxidation. And then if you remember my comparison with price, chlorine, its oxidation number went down. So that is what we call reduced. Think like price reduction, the number is going down. So that's what we call, again, reduced. So losing electrons is oxidation, gaining electrons is reduction. We have a saying to help you guys remember that, and it's Leo says Ger. So Leo the lion says Ger, where Leo stands for losing electrons is oxidation, gaining electrons is reduction. Now be very careful because we're typically used to gaining being a positive thing. Wow, you gained an award or something, that's positive. For this, gaining electrons are negative, so gain is a negative thing. When they gain electrons, that number goes down. So just remember that our electrons, since they are negative, gaining them makes it go down. Okay. So reduction is gain of electrons are negative. That's essentially what that was talking about there. So what I want you to do is, again, pause the video in a second. You're going to answer all these questions. And then once you have answered the questions, you're going to play the video and I'll talk you through the answers to these questions. So go ahead and pause the video, answer the questions, and then once you have done answering them, come back for the answers. So for the answers for this, it says which change occurs when an SN2+ ion is oxidized to SN+4. So if I'm looking at the charges here, SN2+ to SN+4, if I were to put this on a number line, I started at 2+, and I went to +4. I ended at +4. So if I look at what arrow I followed the arrow pointing at oxidation. So when I went from +2 to +4, that tin, which is SN, lost 2 electrons, and since it lost electrons, loss of electrons is oxidation. So for this answer, 2 electrons are lost. Again, redox, we're looking at exchange of electrons. We are not looking at protons. So even though I know it's tempting to say that 2 protons are gained because we see it go up by +2, don't forget from our periodic table unit, when you gain protons, you completely change the element. So it would no longer be tin, it would be a completely different element. So we're only looking at change of electrons when we're looking at changing oxidation states. It says when a substance is oxidized, so think oxidation, Leo, losing electrons, oxidation. So Leo loses electrons. For number 3, it says given the reaction, the substance reduced is. So in this scenario, the only thing without an oxidation number listed for it is iron. All the other ones, they did the hard work for you. They told you tin is +4 on the reactant side and +2 on the product side, and they told us iron on the product side is +2. Iron as a solid is just by itself, that is 0. The reason why the other things have charges is originally they were bonded to something, and whatever they were bonded to, since it says aqueous, when they dissolved in water, they split off from whatever the other anion, that negative ion is, that they were bonded to. So it's just those positive ions, but they do have charges because they did gain or lose electrons. In this scenario, they all lost electrons when they were originally bonded to something. For this, the substance reduced. So reduced is GR, gaining electrons reduction. So I'm looking for the thing that gained electrons. Now, the substance this happens to is always a reactant. So a substance that is oxidized or reduced is always on the reactant side. So automatically, I can cross off anything that is a product, number 3 and number 4. So then for number 1 versus number 2, I'm looking iron in this scenario goes from 0 to +2. And tin goes from +4 to +2. So iron increases in oxidation number, which means it lost electrons. So iron is our Leo, losing electrons, oxidation. And then tin gained electrons because its oxidation number went down, so that's our GR, gaining electrons, reduction. So the thing that was reduced was the tin, because its oxidation number went down from the reactant side to the product side. For number 4, it says given the reaction, which substance undergoes oxidation. So now again, I'm only looking at the thing that undergoes oxidation is a reactant. So anything that is a product, I can cancel out. Now, in order to figure out my actual answer, I have to assign oxidation numbers. So sodium by itself is 0. Hydrogen by itself is 0. I automatically kind of start with those so I don't forget that. And then after that, I move on to my compounds. Oxygen likes to be -2. Hydrogen likes to be +1. So that works out where my total charge is 0. If it didn't, then I would have to go back to my hierarchy of rules and see who gets to be what they want to be. For sodium hydroxide, sodium is a group 1 metal, that's going to be +1. Hydrogen likes to be +1, oxygen likes to be -2, and again, all of that works out to end up being 0. So the one that undergoes oxidation, sodium in this scenario goes from 0 to +1. Hydrogen has 2 options. It's either going to go from +1 to +1, or the one we actually care about, hydrogen is going to go from +1 to 0. That's where we see that change in oxidation number. And then oxygen goes from 0 to -2. So sodium and hydrogen change oxidation number. Sodium's oxidation number went up, so that is what we can call Leo, losing electrons, oxidation. Hydrogen's oxidation number went down, so that is what we call GR, gaining electrons, reduction. So since it went down, it's a reduction. For this question, it asks which one undergoes oxidation, so that is our sodium, because its oxidation number went up from the reactant side to the product side. For number 5, it says in the reaction, the copper atoms are blank when they blank blank. So in order to do this, I need to assign oxidation numbers. So copper by itself is 0, silver by itself is 0, and then if you look, they give us oxidation numbers for the other elements, or ions, I should say. So copper goes from 0 to +2. Silver goes from +1 to 0. Okay. So copper's oxidation number went up. That's Leo. Silver's oxidation number went down. That's GR. This question is asking about copper. So copper's oxidation number went up. So that means that is Leo, losing electrons is oxidation. So it's oxidized when they lost electrons, and they went from 0 to +2, so they lost 2 electrons. for number 6, it says in any redox reaction, the substance that undergoes reduction will, so reduction is GR, gaining electrons reduction. So in a redox reaction, the substance that undergoes reduction will gain electrons. As a result, the value of the oxidation number will decrease. Think price reduction. And then number 7, given the reaction, which statement correctly describes what occurs when a reaction takes place in a closed system? So closed system means things can't escape. Remember equilibrium, we said it has to be closed so things can't escape. So ignore that part. I just want to know what's oxidized and what's reduced. There's not going to be any change in mass, because if you remember, redox reactions conserve mass and charge. So with this, it's going to be either number 1 or 2. So zinc by itself is 0, hydrogen by itself is 0. Hydrogen likes to be +1, which means chlorine is going to be -1. When you're balancing, a couple things to note. Ignore the coefficient. Don't use that to help with your balancing of oxidation numbers and charge. And just the bottom number needs to equal 0. So that total charge needs to equal 0. Your oxidation numbers do not need to equal 0. And I'm going to show you that in a second. So chlorine, let's look between zinc and chlorine. Zinc only has one oxidation state and chlorine has multiple. So zinc will be +2. So that's going to be +2. Chlorine overall is going to be -2 charge to neutralize that +2 charge, which means each chlorine is going to be -1. So if you look on the top here, my oxidation numbers don't have to equal 0 when I add them together. The total charge, which is on the bottom, does. Okay, now that we've determined oxidation numbers, we are going to look at what's gaining or losing electrons. So zinc goes from 0 to +2, and hydrogen goes from +1 to 0, and chlorine goes from -1 to -1. So I don't care about chlorine, that's not changing. But my zinc and my hydrogen change. And it looks like I'm looking specifically at zinc. So zinc goes from 0 to +2. If it's increasing oxidation number, it's LEO, losing electrons oxidation, which means it should be 1. Okay, that is it for the notes.